This is the answer to the Chapter 11 video assignment 1. The question states, at body temperature, 37 degrees Celsius, the Henry's law constant for dinitrogen in water is 3.8 times 10 to the minus 4 molarity per atmosphere. Calculate the molarity of nitrogen gas N2 in blood that is in contact with air at atmospheric pressure, 1 atmosphere, and also calculate the molarity of N2 in blood that is in contact with air at 4 atmospheres. The pressure is T depth of 100 feet. Determine the volume of nitrogen gas that will be released from 5 liters of blood, roughly the amount in a human, if the deep sea diver rapidly ascends to the surface and the air goes from 4 atmospheres to 1 atmosphere. If this escape happens in the form of bubbles in 1 millimeter diameter, how many bubbles per liter of blood is this? So this question is kind of an interesting phenomenon called the bends or decompression sickness, which is really a fascinating thing. So I kind of go through the math here and solve it. First, it wants us to find out how much oxygen is in blood at the different pressures. So using Henry's law equation here, we have the solubility of whatever it is, the molarity, equals the Henry's law constant times the pressure. So for 1 atmosphere, just normal atmospheric pressure, we have the constant 3.8 times 10 to the minus 4. It's molarity per atmosphere, which is equal, of course, to moles per liter atmosphere, times the 1 atmosphere. So the atmospheres are going to cancel. We get 3.8 times 1, 3.8 times 10 to the minus 4 moles per liter molarity in blood. Okay. For 4 atmospheres, we have the same equation with the same constant, 3.8 times 10 to the minus 4 moles per liter atmosphere times the 4 atmospheres of pressure, 1.5 times 10 to the minus 3 moles per liter. So next what we want to do is we want to find out how many moles are in all of the blood in the person. So we know there's 5 liters of blood in a human, and we know the molarity of nitrogen in human blood at these different pressures. So pretty simple, we just do this first molarity here, 3.8 times 10 to the minus 4 moles per liter, times the 5 liters, that cancels, giving us 1.9 times 10 to the minus 3 moles of nitrogen gas in blood at 1 atmosphere pressure. Same thing here, the 1.5 times 10 to the minus 3 moles per liter times 5 liters of blood gives us 7.6 times 10 to the minus 3 moles of nitrogen gas in the person's blood. So now we want to find out how much how much nitrogen gas is going to escape the blood when the pressure rapidly changes when they go up too fast. So to do that, we can just subtract off the amount of nitrogen in the blood at this depth from this one. Because when they get back to 1 atmosphere, obviously they're still going to have nitrogen in their blood, the same amount that was at 1 atmosphere. So we just subtract 7.6 times 10 to the minus 3 moles of nitrogen gas minus 1.9 times 10 to the minus 3 moles, giving us a number of moles, 5.7 times 10 to the minus 3 moles of nitrogen gas that will escape the blood. So the other equation I wrote up here that we'll need is the universal gas law equation here, PV equals nRT. So I rearranged it to solve for volume because we want to know, the question asks for the volume of nitrogen gas that escapes, right? We have moles. So volume equals nRT over P. N is our number of moles, we get that from here. R is the universal gas constant, ideal gas constant, 0.08206 liter atmosphere per Kelvin mole. And then the temperature, body temperature is 37 degrees Celsius. So I just have 37 plus 273.15 Kelvin, right? We need absolute temperature for the units here. All that over, it'll be back at 1 atmosphere when it gets to the top. So that's the pressure it'll be at. Solving that gives us a value of 0.14507 liters of nitrogen gas. Now taking significant figures into account, we've got just 2 significant figures. So for this answer, 0.15 liters of nitrogen gas will escape the blood in the ascent, okay? Now, the question then wants to know how many bubbles will that be? So to solve that, we can find the volume of each of those little bubbles. It says they're 1 millimeter in diameter. So the volume of a sphere is 4/3 pi r cubed. So 4/3 pi, and then the diameter is a millimeter, so 1/2 millimeter here for the radius cubed, yields a result of 0.523599 millimeters cubic millimeters. So to solve, we're going to need to get that into liters so that we can use the value over there that we got for the total volume. And there's 1 million cubic millimeters in a liter. So doing some just unit conversion here, we divide 1 million off of our value there, giving us 5.23599 times 10 to the minus 7 liters of nitrogen in the bubbles. Okay, so now we know the volume of the bubble, and we know the total volume of air. We can find out how many bubbles that is. So I'm using the value here before we did the sig figs, just because we'll apply sig figs at the end. So 0.14507 liters, total liters of nitrogen gas, divided by the volume of a bubble, 5.23599 times 10 to the minus 7 liters, gives us 277,063 bubbles. So that's still for 5 liters, that's for all of, right, because this was all of the gas that was going to escape. So we need to, the question asks for bubbles per liter. So we got to divide that by 5. So we take this value, 277,063 divided by 5 liters, gives us 55,412. Now sig figs are going to be 2 again here, so it'll be 55,000 bubbles of nitrogen gas per 1 liter of blood. And so those are the solutions. There's the molarities there at the different pressures or depths, the total volume of nitrogen gas that will escape the blood, and how many bubbles per liter that will be.